present our work Parameterized Property Testing of Functions. This is a joint work with Sofia Rasodnikova and Nitin Verma from Penn State. So let me start by giving a short introduction about sublinear time algorithms. Sublinear time algorithms are randomized approximation algorithms that run in time sublinear in terms of their input. And as they are sublinear, they cannot examine the entire input. They only have just enough time to access a small fraction of the input. The complexity of sublinear time algorithms is usually measured in terms of the size of the input. So our work is motivated by the question, is the input size always the right parameter to express the complexity of sublinear time algorithms? We reconsider the way in which the complexity of sublinear time algorithms is expressed. Even the notion of sublinearity is defined in terms of the size of the input and not on other parameters that might capture the input complexity. So our work is on parameterizing sublinear time algorithms, wherein the main goal is to find input parameters tailored to the combinatorics of the specific problem and use these parameters to get more efficient algorithms. As bounds in terms of the input size may not always capture the fine-grained complexity of the problem. So in spirit, our work is analogous to the parameterized complexity for classical algorithms. And some example of parameters that are useful for sublinear algorithms are the number of distinct values in the input, and in case of graphs, bound on the maximum degree. And in this work, we mainly focus on the property testing model. Property testing model was introduced by Rubinfeld and Sudan and Goldreich, Goldwasser and Ron. The central problem in property testing is to decide with high probability if an input object satisfies a property or is far from satisfying it. Let me explain this with a small example. So this is an example of an array whose elements are in sorted order, or in other words, the array satisfies the property of sortedness. Whereas this is an example of an array that is not sorted. And in fact, we have to change at least half fraction of elements. Out of each consecutive red-blue pair, you have to change at least one element to make it sorted. And this is one way of making it sorted. So we can show that at least half fraction of elements need to be changed in this array. So the property of the generalization of sortedness is the property of monotonicity on functions, which was initially studied by Goldreich et al. And Ergun et al. And it has been studied extensively in the field of property testing, and there are dozens of papers on it. So coming back to property testing model, there is an unknown function f which we wish to test for a property p. The algorithm or tester for the property p takes in as input the approximation parameter epsilon and the size of the domain n, and it is given oracle access to the unknown function f, wherein it can query a number of points, and the oracle returns with the function value at each of these points. And at the end of the process, the tester has to accept with high probability if f satisfies the property, and reject with high probability if f is epsilon far from satisfying property p. So f is epsilon far from satisfying property p if at least epsilon fraction of values in f need to be changed to make it satisfy the property p. So recall this example in which this array is half far from sorted. So in our model, in addition to epsilon and the size of the input, the tester is given an additional parameter r, which is used to measure the complexity of the algorithm. The goal is to find a parameter intrinsic to the problem so that it captures the complexity better than the size of the input. So a related concept of parameterized testability was studied by Iwama and Yoshida, whose work appeared in thesis 2014. So their focus was on property testing variants of NP-hard graph problems. And the parameters that they used are from classical parameterized complexity, which are usually NP-hard to compute. In contrast, our work is on finding the right parameters for property testing problems, and these parameters are tailored to sublinear computation. So let me give some parameters for property testing now. The parameter that we studied in this work is the image size, which is basically the number of distinct values that the input function takes. And this parameter is suitable for sortedness of arrays, monotonicity over hypergrids, and convexity on the line. A related parameter is the image diameter, which is basically the difference between the highest and the lowest value that the function takes, and it has been used for testing Lipschitz property on the line by Ja and Raskolnikov. A parameter that is related to graphs is the bound on the maximum degree, and it has been studied extensively by Goldreich and Ron in their bounded degree graph model paper. So here's a short summary of our results. So as Aviyat pointed out, the testing sortedness of arrays with at most r distinct values can be done in order of log r time, and sortedness was considered settled for almost over a decade. So there's a matching upper and lower bound of log n, and we were able to circumvent this lower bound by considering different parameter, which is the number of distinct values in the arrays. And a similar picture emerges for sortedness tester with only access to uniform samples. So we were able to replace the input size n with the number of distinct values in the array r. And it is also true for monotonicity on higher dimensions and convexity. So I would like to conclude my talk here with an open question. Can we find other parameters that help us understand sublinear algorithms better? Thank you.
So when you're given a list to be sorted, you're not also given R, the number of distinct elements, but you're still able to solve it in log R time, right?
So the R will not be exact, so it's just an upper bound on the number of distinct elements. So if you know that these are the set of elements from which the list can be there, then this is pretty easy.